Hello everyone. In this video I'm going to just go over um, two things in the measures of fit. I think I was like running so fast over this last part of the lecture, which is basically the measures of fit. So as you noticed, there are some of these measures that are kind of easy to understand. So I will not go again over um, count R square. So I'm not going to go over this again. I already did it. It's kind of easy to understand. I'm not going to go over wall test. It's easy to understand, similar to the F test, and it's almost the same as F test in large sample. Okay, let me go over the pseudo R square. And the pseudo R square, as I mentioned in class, it's computed as a ratio between two log likelihood functions. So it's 1 minus the log of f, where f I call it likelihood function. As I said in your textbook, you will find this one called L. I'm not sure why the author decided to call it L, but it's mostly called F. It doesn't matter as long as you understand the idea of the full model over the log likelihood function of the intercept. Okay, so when I say intercept, this is kind of the benchmark that we're going to compare with. And this is actually the default in Stata. So when you run the regression, you get the pseudo R square, understand that they have a default as intercept. Of course, we can do a default as a model which has 3 x's versus a model that has 2 x's, but this is, you have to kind of override the default. So as I said, important things about this pseudo R square is you understand that the likelihood function, the one I wrote on the board, which has a p y1 all the way to yn given the x's, you can say x1 to xk. Okay, so this is the likelihood function. And as I said in class, this likelihood function falls between 0 and 1. Okay, so the likelihood function, if it falls between 0 and 1, then it's log of the likelihood function. Let me write a bracket dot, which you understand it's basically everything here is in here. So the log of the likelihood function is basically less than or equal to 0. Okay, so if you take the log of a number that is between 0 and 1, then you will get the log of it, the log of any number between 0 and 1, you will get it as either negative or 0. So what does that imply? This implies that if I have a model with low likelihood, this implies large log likelihood. And the opposite is true. If I have a model with large likelihood, then it has a small likelihood. When I look at these two models, this one versus this one, if I want to make sure that whether the full model improves the fit over an intercept, then it has to be the case that this number is smaller than this number, so that I can get a small ratio that is out of 1 would be relatively a big number. So if I'm saying that this is the log of the likelihood function, that I want it to be low, then I need the likelihood function to be high. Okay, so how can we say this? So basically we say that a small ratio of the log likelihood function. By now you understand that this is the log of the likelihood function. Basically indicates that the full model is better, right? Which is actually what we want. If I'm using some axes and I want to make sure they are improving, then I want to see something like that is better than the intercept model. And this is kind of your benchmark. Okay, so I just wanted to write this in details because I think I didn't write it on the board. I just explained it and I didn't have the time to write it. Again, as I told you in class, this pseudo R-square is called in Stata because it's actually made by this person, McFadden, and it's called the McFadden's pseudo R-square. Okay, and then I told you we have an adjusted version of it if I divide the numerator by k. So if I divide the numerator by k, which is the number of x's in the model, then I will get the adjusted version of the McFadden's. Again, as I told you in class, there are so many other R-squares that are computed based on likelihood functions, different versions of it, but these are the ones that are mostly popular, mostly used, the McFadden's and the adjusted McFadden's. Okay. The other thing I wanted to mention is about the likelihood function. I'm sorry, the likelihood ratio test. So this was test. So the likelihood ratio test, again, I did kind of write it very fast. This was number test. So I have 1 and 2, and we have the pseudo R-square, which is the McFadden's, and we have the adjusted. The adjusted is number 4. Okay, so we have the adjusted, and number 5 is the likelihood ratio test. And as I mentioned in class, I wanted to think of the likelihood ratio test as very similar to the R-square idea. I'm taking a ratio of a full model divided by the intercept. What they're doing is very similar, but they're taking the log of a ratio which has a likelihood function in the numerator. So let me show it to you. So it's basically the likelihood ratio test would be equal to the log of, let me call this one f. Again, notice that it's not log f, it's f. So this is the likelihood, not the log. Function. Okay, and this one is the unrestricted or the full model minus the likelihood function restricted, and to make it to have a like a chi-square distribution, so it's squared, and like this. So when you take something like this, when you take the log, when you take this log inside these brackets, then it would be equal to 2, right? And log of unrestricted minus the log of restricted. Okay, so actually, you know what, I said something wrong here. Let me correct myself. I felt like I'm saying something wrong, so there is something here wrong, because this is a division. So this one is the log of, sorry. So this one is equal to the likelihood function, so it's f likelihood function of the unrestricted over the likelihood function of the restricted squared. Okay, that's it. So when I take this log inside, then I'm going to have the 2 out as here, and then log of fu. Let me be kind of more organized. So I'm going to have it like 2, okay, and then I have a bracket of f or log f unrestricted minus the log f restricted. Okay, and this is what I had on the board, so let me write the u nicely. So it's gonna be like this. So the u here, unrestricted, the 1r here is the restricted. You can think of this one as the full model, and you can think of this one as the model with the intercept, because I'm restricting the variables to be equal to 0. Okay, so of course this one has a chi-square distribution of how many restrictions I'm testing. So if I have here 3 x's and here I have intercept, then I'm kind of having 3 restrictions. So we're going to have this q. Okay, it's q because I noticed one of the students are writing this as 9. It's not 9, it's q restrictions. So it's very important to understand that the log of the likelihood function of the unrestricted model is greater or equal to the log of the log of the likelihood function restricted. So that means that this likelihood ratio test is non-negative, okay, and it's actually strictly positive. So it's usually okay, strictly positive. Okay, so why is that? Because as you know, the log of the likelihood function is always negative. Okay, so the log of the likelihood function, these are always negative. Why? Because actually the numbers that I'm taking log for, which are inside here of the likelihood function, are always positive. Like the y is 0 and 1, for example, and the variables inside are either 0 and y or positive numbers. So you're taking a log of a positive number, then it's basically going to be negative. Okay, so the likelihood function is always, the log of the likelihood function is always negative number, because the y is positive, it's a 0 and 1, and the variables inside this function are positive. So their natural log is negative. Okay? Alright, so I'm going to send you this, and I'm going to send you an example. Just thinking for an example, maybe I will choose the one in your textbook and explain it so that when you read it, it kind of be easy. So I'm going to do that in a few. Okay. All right.